So basically, in the outline, I'll first, basically briefly touch upon, say, RF power combining circuits. Well, of course, I mean, most of us would know that. So, I mean, this is just a brief, introduction there. So then I would like to introduce spatial combining. So under spatial combining, let's so basically look into a few publication review and then say commercialized products. So the spatial combining initially when it was actually published, I mean, though it was called spatial combining, it was actually basically combining things. I mean, combining the fields, say using small dipole elements in a constrained medium, like say, like an oversized waveguide. So then after that, we'll touch, say I mean, a brief review of the spatial combining in free space. I mean, I think a lot of us today will actually know about antenna arrays, etc. I mean, this will just be a brief insight as to how that is actually applied to spatially combine outputs of RF power amplifiers. Now, until this point, the focus would be, say, just on combining, I mean, RF power. Now, beyond that, so beyond this point, I would like to extend this to to commercial wireless communications. That's where one could actually apply spatial combining to, I mean, to basically to scale power as well as bandwidth, along with a few experimentally validated cases. Of course, these experimental validations were not conducted in my present company, Qualcomm. So these were basically conducted in academia. I mean, prior to me joining Qualcomm. Well, I mean, due to legal constraints, I'm unable to, basically show anything of my, done with my present employment. But well, but anyhow, these would be basically good examples. I mean, to illustrate the concept. So, well, first of all, RF power amplifier. So the thing is, I mean, if we look into the block diagram of of a wireless transmitter, this is what actually consumes the highest power. So, I mean, it is the RF power amplifier which essentially boosts the signal, so that one can actually get the wireless communication range. Now, from a circuit perspective, basically high output powers basically imply high current handling capabilities. So now, say if we look into a typical transistor structures, so then basically high current handling capability implies that the channel current that the transistor should be capable of handling is actually quite high, so which can range to amperes. And another significant part in power amplifier is that the power amplifier is power efficient only if it's operated in saturation. This is unlike the linearity requirements in, say, in baseband or in small signal amplifiers. Now, in an integrated circuit, say, be it monolithic or even non-monolithic microwave integrated circuits, say several amplifiers are, I mean, usually operated in parallel, and the outputs are combined to basically to feed a common load, so that the high output power is obtained. Say, I mean, a typical RF power amplifier design, say, with multiple amplification stages, will look something similar to this. Say, I mean, that's where we have an input power division network. Then we have, say, initial driver amplification stages, and then this is again split, and then we have, say, 4 parallel output amplification stages, and all of them are combined into the load. So now the thing is, I mean, very popular schemes, particularly in the RF sector, are basically using binary structures. That's where the number of branches is essentially a power of 2. Now the thing is, one of the constraints with this approach is that the overall bandwidth is constrained by the bandwidth of the combining circuits as the first thing, and secondly, the thing is, the failure of any branch will actually be a hard failure. Means essentially the power amplifier will be inoperative. So now say consider, for example, we have, say, 4 of these output power stages. So now say if any of them backs off, so then basically the output impedance seen here, I mean seen from this point, is actually increased. So then the load matching is gone. Uh, and over and above that, that is as one actually goes up higher in frequencies, the combining structures or the planar combining structures like microstrip or strip line basically get lossy. I mean, that's primarily due to the high loss tangent the substrates. And secondly, the power handling capacity of the substrates will be limited, because the thing is, I mean, once we go higher in frequency, we need to reduce the dielectric thickness, mainly to reduce the dielectric losses, and at the same time reduce the, width of the transmission lines, so that so that they don't start radiating. Because if the width and length are comparable, then that's actually going to act as a small dipole. Now, an alternative to this, actually, that has been considered, say, for the past 2 decades, but primarily limited to academia, has been spatial combining. So, in spatial combining, essentially, uh, we have multiple amplifiers in parallel, but then these outputs are actually combined without any physical circuit path between them. So, typically, uh, there are multiple ways of doing that. So when it was initially introduced, so it basically consisted of something like an oversized waveguide, into which multiple parallel uh, amplification stages were inserted, and then the structure was essentially fed using a horn antenna, and the amplified structures were again collected using a horn antenna. So that was how the thing was actually conceptualized, say about 2 decades ago. Uh, Now there are commercial projects. Now there are commercial different products which will be looking in the upcoming slides. Now, another way of spatial combining is basically combining in free space. So essentially, all the beamforming transceivers that are actually currently operational for 5G, they all essentially do spatial power combining. That's where there are multiple, say, there are multiple antenna elements. Each one connected to an RF power amplifier, and then a progressive phase shift is actually applied to each of the parts. So that the power is maximum at a specific, I mean, at a at a specific angle in space. So we'll be touching upon this. So now, spatial combining in a constrained medium. So this is how the thing actually started. So what you can actually see here is essentially an oversized waveguide. So by the term oversized, I mean that the dimensions of the waveguide are much larger than the fundamental, than the fundamental mode of operation. Say for rectangular waveguides, usually the fundamental mode of operation is the T10 mode. So, so basically there is a structure which is made much wider than that. Now, the input signals are actually fed using a horn antenna, and along the cross section of the waveguide, an array of dipoles, an array of input small electric dipoles are connected to individual amplifiers. Whose outputs are again basically connected to electrically small dipoles. So the way this works is the field from the field that is instant into the waveguide is essentially sensed by these electrically small dipoles. So then these are subject to amplification, and then they're retransmitted towards the output horn. Now, though though this is not in free space, the term that was actually used for this was actually spatial combining. So the same has actually remained. So if we get into the history, one of the first successful spatial combiner implementations was actually in the year 2000 for an American government-funded project called DARPA. So here is a publication that we could review briefly. Now, again, the thing is actually, I have pasted hyperlinks here because I couldn't actually get permission to reuse any of these contents in the screen. So therefore, I decided to to directly provide web reference, so that we could take a look here as to what we are trying to see. Excuse me. So in this publication, actually, the authors review, they give an overall insight of the scheme here. So they basically look at it from a quasi-optical perspective. So well, it was young then when it was published, but as on today, we have companies which are actually manufacturing these even for spacecraft sort of applications. So the way the way this publication basically goes is that it first introduces the concepts of, say, power combining. So I mean, similar to what we had earlier, and then introduces the concept of spatial combining. So I mean, this is very similar to, I mean, what I introduced in the, I mean, in the preceding slides. So the way this works is basically there is an array of there is an array of amplifiers here. So in this case, I mean, they have basically made an experimental study of number of amplifiers versus the normalized output power. So the term normalized output power implies, the power of one device multiplied by the number of devices here. So I mean, that's what that is the terminology used in this publication. So one can see that, compared to planar combining structures, actually, they've been able to achieve up to 90% of combining efficiency, as per this graph here, say with about 64 elements. So the principle that they apply is very similar to what we just saw earlier. So, I mean, since this is in the higher gigahertz range, say, I mean, it is in the 90 gigahertz range here. So, I mean, they have actually used microwave lens antenna mainly to get the beam into into an active antenna array. So there are multiple ways in which this amplification array has been designed here. So one of the ways is actually called the tile structure or the tile array, and the other one is called the tray array. So in a tile array, it's essentially a planar array of antennas. Say one of the so one set of antennas basically faces the feed horn. So this is connected to the gate of the transistor, or basically the input terminal of an amplifier. So then each of those outputs are connected to another output antenna element. So thereby it forms an input array and an output array. In between, the amplifiers are sandwiched. So this was one of the first spatial combiners that was actually built. So here is an example as to how they have implemented the array. So basically, they've gone with a differential amplification structure. So you can see that the drain terminal, of the transistor here is actually, the sources are actually coupled. So you can see that, the two drains are in opposite polarization, which actually forms a small electric dipole. Similarly, you can see that the inputs are again in opposite are in electrically opposite potentials, and with, say, individual quarter wave lines here. I mean, it's not exactly quarter wave. So basically, there is a small electric dipole at the input, as well as one at the, output. So the way they operate here is that, instead of sandwiching the transistor elements or the active elements, say, between two antenna arrays, they try to make a more optimal structure. That's where they receive in one polarization, say that is an horizontal polarization, and then they transmit to the output horn in the vertical polarization. So they actually have polarizers in between. So as can be seen, as can be actually seen here. So with this, they're able to, they're able to achieve, close to an octave of operation. So well, that can be seen in the results below. So now, similarly, they've also experimented with other structures here, like say, instead of using wire dipoles here, they've also used slot dipoles, and instead of using electrically small dipoles, they've actually used half-wave dipoles here. So which actually makes the radiation efficiency higher. One of the, an alternate way to accomplish combining is by, well, because that is something which has to, so what we saw earlier, the tile structure is something that has to be physically fixed at the center of the cross section. So whereas here, uh, they actually achieve the same by, by having, say, higher number of amplification stages, but what they have is they actually have a traveling wave antenna structure. I mean, which is essentially a fin line to harvest the E field that is in the waveguide. So then the harvested field basically creates a potential in the antenna. I mean, it basically makes a current flow in the antenna, then which is amplified, and then which is again pushed. I mean, pushed to the other side of the waveguide. So with this, actually, they were able to handle an input power up to 30 dBm, that is 1 watt. So which is actually, I mean, which is an amazing thing, say, particularly from the MMIC perspective. So overall, the thing is, they've actually experimented this in multiple bands. So the lowest band has been X band. That's where they've been, I mean, they've been able to achieve an output power of 20 watts, say each with, say, 5 watts gallium arsenide MMIC amplifier. And so here is an interesting application. So which is by Lockheed Martin. So which is a 25 watts K band amplifier. I don't know what the application is, well, because I mean, since this was funded by the US government, they wouldn't reveal that. So to me, this appears more like, say, I mean, could be either a satellite uplink, or probably it could be, I mean, a point-to-point military relay station, or it could also be for an antenna. I'm not exactly sure about the application. So here you can see that they've actually used the tile structure. That's where they have the input waveguide coupled with a horn. So then they have the antenna array with the amplifiers, and you can see that the amplifiers are orthogonally polarized. I mean, sorry, the input and the output elements are orthogonally polarized here, as you can see. And they've been able to achieve something like 25 watts at Ka band, which is quite a high power. And so here are some of their input-output graphs. So where one can see that they've been able to achieve, say, close to 30 watts of output power. So here is another validated case. That's where they show up to 35 watts at 61 gigahertz, and they indicate a power. And for the previous case, say for the previous Lockheed Martin case, they indicate a combining efficiency of 80%, which is again a phenomenal figure in the millimeter wave range. Now, coming back to the slides. I'm sorry for the. Now, those were things actually that were originally published 2 decades ago, but then they themselves actually concluded that they were, I mean, they were in very, very infancy. I mean, that they were in infancy, and then the technology was yet to mature. But today, we have this company Corvo actually having spatial amplifiers or spatially combined amplifiers, but using a cylindrical waveguide. Uh, you can see that they're able to get up to 250 watts of power at 35 gigahertz using, say, 16 parallel stages. Another major advantage of this scheme is basically soft fail, because if any of the amplifiers in the, I mean, in the parallel structure fails, so it is only that part that fails, but then that is not going to shut down the, I mean, the entire PA. And they've also achieved nearly a decade of bandwidth in some of the models. So, well, one could just, I mean, I'll also be sharing these slides shortly, but one could actually see the salient features on the website here. So you can see that they've actually achieved something like 300 watts over a decade, over close to a decade bandwidth. That is from 2 to 18 gigahertz with spatial combining. So what was in infancy about 2 decades ago is now a premium product. So, but then, I mean, now since we reviewed both of them, actually, so some of some of what we could actually conclude is that so spatially combined power amplifiers in a constrained medium have basically matured from concept to commercial products. I mean, the proof is right there. So as of now, these actually provide the highest efficiency compared to, I mean, not high, need not be highest, but higher than any planar structure that is state of the art today. Now, they also provide output powers in the range of hundreds of watts, primarily due to the high power handling capability of waveguides. But then we also have a few, I mean, say demerits here. The thing is that it's currently not feasible for commercial user equipment because these are going to be highly expensive because waveguides basically involve quite an amount of machining to get the surface roughness very low. That is mainly to avoid, or that is mainly to mitigate the field perturbation and conductive losses. But it is however apt for applications in millimeter wave infrastructure, like say like base stations or satellite communications. So this is where the technology stands as on today. But well, nevertheless, actually, in the next couple of years, I mean, with say with metal 3D printing, I mean, being popular these days, so well, the cost could actually come down. Now, so what we saw there, was essentially just a combining mechanism for, I mean, for output. I mean, that is mainly to get high output powers. Now the thing is, in none of these we actually saw any mention of say parameters that are related to wireless communications like say like peak to average power ratio, etc. Because the thing is, when it comes to wireless communications, particularly the terrestrial ones, we are not going to operate with constant envelope modulated signals. Whereas I mean most of our signals here are essentially OFDM, so which exhibit a high peak to average power ratio. So now that being the case, can amplifiers like these actually be applicable, or can spatial combining be applicable to amplify modulated signals faithfully and efficiently? So I mean, this is a question. So one of the military suppliers called L3 Communications has actually come up with such a scheme. So this essentially resurrects a century-old scheme called outphasing. So in outphasing, what's actually done is any envelope modulated signal, say having an instantaneous amplitude of say A of t, is converted to two constant envelope but continuous phase modulated signals, say S1 of t and S2 of t, by adding an outphasing phase in one of the paths and by subtracting a phase in the other path, or basically by creating a phase lead and a phase lag in two paths. So the extent of the phase lead or lag is essentially the inverse cosine of the instantaneous amplitude to the maximum amplitude uh, of the signal for the specific modulation scheme. So now since the signal is actually decomposed into two constant envelope modulated schemes, the two can actually be amplified, say using high efficiency classes, like say like class C or class E. Well, of course, in millimeter wave, class E hasn't been very feasible. Uh, so this is where, this application of spatial combining could be seen. So here is a patent by L3 Communications. So if you see what they're actually doing, so they're initially decomposing the signal, say, I mean, a varying envelope signal or an envelope modulated signal into two parts, say S1 and S2. Now, they're applying the real part of S1 to one of the arms, say, I mean, to basically, to an electrically small antenna in in an oversized waveguide, similar to what we saw with Spatium. And at 90 degrees to that, they're actually applying the Q part. Similarly, in the two opposite arms, they're actually applying the S2. I mean the I and the Q part of S2. Now the signal. I mean now these signals actually combine in this constrained cavity. And then the combined output is actually harvested using a coaxial probe along the axis of the, of the combining structure. So with this, they're actually able to achieve high powers with high efficiency, even with, even with signals that are, that usually require high linearity. So basically, they're achieving linear amplification with nonlinear components here with high efficiency. So this is a patent by L3 Communications. Now, having seen spatial combining in a constrained medium, say like in oversized waveguide, so there are also, other classes. There is also another class of spatial combining which is in free space. So as on today, whatever we see in the form of, say, beamforming is essentially, it's essentially spatial combining of the outputs of, say, individual transmitted chains. But the thing is, it is actually, the combining is accomplished in the far field of the individual antenna elements. Now, if you look into the block diagram of this, say typically the digital modulation is taken care in the DSP, and then in the transmit chain we have the digital to analog converter and the up converter, and then we have the driver amplifier. So then at the output, then say, because typically in millimeter wave, the the duplex scheme is, it's usually TDD, it's time division duplex. So it's either the transmit or the receive which is active at any given time. And then we have gain elements and phase elements like this. So in order to get a beam maxima at a specific point, so there is a progressive phase shift applied such that, say, phi 2 minus phi 1 will be equal to, say, phi n minus phi of n minus 1. So there are two types which are normally used in the present day communications. Say, that's where we have the analog beam forming and the digital beam forming. So in the analog beam forming, essentially, we don't have one digital signal per path. So basically, one digital signal drives an array of RF chains. So this is much more cost effective, and essentially, it's also more power efficient. But then the problem is now, one might actually wonder, why does one need attenuator here? If the objective is to increase power. Now the thing is, say if you're looking at an antenna array here, the thing is, we would actually like to limit the radiation in side lobes because these are not in the direction of the intended radiation. But then one could actually try to correlate this, say, to sync. It's like this. So, if we have a rectangular spectrum, we end up with the sync pulse in the time domain. So similarly, if we have a uniform excitation of antenna elements, so then the spatial distribution is going to follow a sync function. So one of the ways to reduce the side lobes is by, providing a non-uniform excitation. Let's say instead of a, instead of a rectangular spectrum, say we have something like a cosine spectrum, or a cosine on a pedestal, or a trapezoidal spectrum. Now, a second class in beamforming is, well, of course, beamforming is not the focus of the session, but I'm just touching this upon, mainly for the upcoming slides. So the second section is, the second type is essentially digital beamforming. So that's where each transceiver element is driven by a specific digital chain. So that's where we have a DSP, and then there is a digital chain in each path consisting of, say, digital to analog converters, IQ modulators, and subsequent up converters. But then now, since it's in digital domain, it's actually much easier to maintain, say, the beam integrity, because one could actually apply very fine shifts of phase and gain control. But then, of course, this comes with the cost of basically operating n number of digital front ends, n number of up converters and down converters. But then this is easier to implement schemes like digital pre-distortion, mainly to linearize the power amplifier, if any. On the other side, from a circuit perspective, it can be a nightmare to circuit designers. That is mainly to distribute the clock and considering the EMI EMC aspects. So, see, the thing is, now, the reason I'm mentioning, how to basically, design an array for, say, for a specific EIRP is mainly to, provide, say, an insight into what is actually coming next. That is, combining RF power amplifiers in the free space. So typically, if we have a rectangular antenna array, so usually the thing is the beam swinging. Usually the beam sweep range in the horizontal domain will be plus minus 60 degrees from the normal or from the bore side, and usually in the vertical domain, that is along the elevation, it's usually around 22.5 degrees plus and minus. So that being the case, one can actually have greater spacing in the vertical domain compared to the horizontal domain. So typically, the antenna gain or the antenna directivity in a specific axis actually depends upon the number of elements, the spacing between them, and the wavelength of operation. So it's basically 10 to log base 10 2n multiplied by d over lambda. That's where d is the spacing and n is the number of elements. Now, similarly, in the other axis, it'll be nx basically. Because considering, say, radiation in the z direction, so the plane is actually formed by x and y axis. Now, directivity is not the gain, because directivity is how directive the antenna is, or the ability of the antenna to focus the beam in a specific direction. But then antenna is also made up of practical elements which are not ideal. Like, say, there are going to be things like dielectric loss, the feed loss, perturbation in the conductor, surface waves, etc. So typically, say for a planar microstrip array, one could actually, one could usually get an efficiency of, say, 70%. So now the antenna gain, the output power in dBm minus the antenna gain is essentially going to be the input power that is actually needed to feed each of the elements. So now, that is going to be the total input power. Now, the input power minus the number of, minus 10 log the total number of elements is actually going to be the overall input power per amplifier here. So one can see that essentially to get an output power of 60 dBm, to get an output EIRP of 60 dBm. So 60 dBm is 1 kilowatt. So for that, what actually one needs to feed in each element is 24. So it's going to be something like about half a watt, say 27 dBm, considering all the losses. So this extra gain, this phenomenal gain primarily comes due to the antenna directivity. So here is a small case study or a publication review. That's where the authors have implemented on-chip antennas in Cmos, and they've been able to achieve output powers up to plus 24 dBm at 95 gigahertz. And they also claim this to be the first spatially combined amplifier in Cmos at W band, say that is at 95 gigahertz. Now again, I couldn't get permission from any of these authors to basically, to reuse any of their contents in the slides. So therefore, I've just provided hyperlinks to each of them so that we can see them, say live in the session. So one can see that they've actually implemented this sort of a parallel amplification. Excuse me. So altogether, they have an array of say 2 cross 4, so totally 8 antenna elements. And then they've actually designed differential PAs. So the differential PAs actually feed, I mean, each differential PA will feed a microstrip patch antenna differentially. And then the entire thing is actually packaged in a, say, in a small form factor, in a rectangular form factor. So this is on-chip implementation. So as on the day they designed, the best antenna efficiency that they were able to get was about 40%. But then, well, I mean, things have actually improved as on today, particularly with the antenna simulation tools that are actually available. So this is the practical implementation of the Cmos chip. So one can see that they actually have differential PAs here, and then each of these lines is actually feeding an amplifier. I mean, each of these is actually feeding an antenna element. So altogether, they have say four horizontally and 2 vertically, so making it a 4 cross 2 array. Now, the spacing that they have maintained is not half lambda that I mean showed earlier. So they have 0.42 lambda in the horizontal direction, and say they have 0.59 lambda in the vertical direction. So, well, of course, I mean, because for IC designers, it's fair to consider this sort of spacing because they also are constrained by the package size and everything. Now, here are some of my simulations of similar, I mean, of antenna structures for similar applications. Say, say about done two, say about 2 years ago. So essentially, the objective was to maintain ability to operate over a wide bandwidth. So one can see that the 10 dB return loss bandwidth, I mean, of each antenna element here, say, is about 10 gigahertz. So basically, everything is operational from 20 to 30 gigahertz. So with uniform excitation, actually, the gain obtained was about 17.5 dB isotropic, say with a directivity of about 18.8, so which implies an efficiency of around 75%. Now, until now, we were only looking at combining power spatially. Now the thing is, we are not going to operate with CW signals. I mean, say unmodulated signals, unless and until one is actually working on things like accelerators, or one or even or one is also not going to operate with say with just constant envelope modulated signals, say like QPSK or 8PSK, unless and until one is actually doing a satellite communication. Now, in such scenarios, I mean, say in the present scenarios, that's where we have say wide bandwidths and also high peak to average power ratios. It would be beneficial to have structures that can scale both power and bandwidth of a system by spatial combining. So that is something that's actually being present here. So the thing is, actually, if we look into even the present 5G features, basically the user equipment data rates range from say from hundreds of megabits per second to multi gigabits per second. and we intend to operate in multiple bands, then we have massive device-to-device communications. And now the key enabler to these, so one of the key enablers to high data rates is essentially wide channel bandwidths, and also schemes like carrier aggregation, massive MIMO. So now, if we look into the generic modulator or a generic IQ modulator, well, because the very first thing that we do in any wireless transmitter is that we modulate the signal. Now, since we are speaking about digital data, so usually our digital data is handled by the DSP, and then uh, on the basis of the bit mapping, on the basis of the bit grouping and the modulation scheme, one actually generates modulation vectors, say, which is essentially an amplitude and phase, so which basically translates into I plus JQ. So typically we have a DSP, a set of, say, a digital to analog converters, whose outputs are combined in a quadrature up converter. This is mainly to yield the required modulated output spectrum. Now, if we look into the bandwidth of the signal that we can actually generate here, one can see that the primary implication here is actually going to be the maximum sample rate at which we'll be able to clock the DACs first thing. Now, one can see that typically high-speed DACs, say particularly those that operate say in multiple gigabits per second, they are indeed interleaved in the time domain. So that's where, here is just here is a case of, say, two DACs being interleaved in the time domain. That's where, say, we have clock distribution circuits, and then we have an analog mux that alternates between the two DACs, mainly to get the analog output. Now, that is one of the ways. Now, here is an alternate way. That is, we do the interleaving but in frequency domain. Now, consider any complex envelope modulated this one signal. If we look into its FFT, or the fast Fourier transform, it looks something like this. So from 0 to, so considering that we have an oversampling rate of 2, say from 0 to fs over 4, we have a region. Typically one cannot operate a Nyquist rate because one cannot actually eliminate the images in the adjacent Nyquist zone with any practical analog filter. So oversampling is required in any case, at least as far as I know. So if one can look into the spectrum of this, essentially, we have half of the bandwidth in the lower half of the Nyquist zone, and we have the other half of the bandwidth in the higher half of the Nyquist zone. Now, this, if we try to modulate, or if we upconvert this using a vector upconverter, this is a spectrum that we are actually going to get. That's where we have the carrier frequency at the LO frequency, and then the overall occupied band ranges from, say, from F carrier minus bandwidth over 2 to F carrier plus bandwidth over 2. Now, instead of doing this directly at baseband, now consider upconverting the signal digitally to FS04. Now, in such a scenario, one can see that actually one has the entire bandwidth in each of the Nyquist zones, but each one is actually, but then one of them is actually centered at, say, FS04, and the other one is, say, centered at 3FS04. Now, these two are essentially images of one another. Now, what if we, now, since we have two DACs here, now, what if we basically generate the Hilbert transform of the first signal in the second path? Let's say, typically we would multiply the I with the cosine phase of the LO, and say Q with the sine phase. So now let's do the Hilbert transform here, which we can get by multiplying I with the sine of the LO and, say, Q with the cosine of the LO. Now, when this is done, now post this, when the two are upconverted, one is actually going to get rid of the image totally. Now, applying the same principle, let's mark the regions, say as 1, 2, 3, and 4. Now, we have the original signal, I mean, that is, say, upconverted digitally, say, I mean, which has the subscript A, and then we have its Hilbert transform, which has the subscript B here. Now, if we extract the two end components and the two inner components and separate them, and if we take their IFFT and apply them to individual DACs, upconvert them, we are only going to be left with the required real part in each of the parts, where the first part basically occupies the spectrum, say from F carrier to F carrier minus bandwidth over 2, and then the other part is actually going to occupy a spectrum from F carrier to F carrier plus bandwidth over 2. So essentially, the thing is, we get the same thing as time interleaving, but we do the interleaving in frequency domain. Now, what is the advantage here? The thing is, because in time interleaving, now say if you have to scale the circuit up, say to wider bandwidths, you need a faster mux. And the thing is, we would also need to distribute these clocks accurately, I mean, to further stages. And moreover, the mux here basically operates at, at the sample frequency Fs, means the slew rate of the mux is going to be critical. I mean, the slew rate of the transistors in the mux is going to be quite critical. Whereas here, we don't need any external mux here. Now each of the DACs essentially operate at half of the sample rate, and then they get upconverted, and then the output can actually be combined spatially. So here is one such demonstration. That's where a SATCOM signal, say a DVB S2 signal, was generated in this manner. Say this was actually the lower half of the spectrum. This was the higher half of the spectrum. The two were, initially the two were subject to in-circuit combining. This is mainly to check the quality of the scheme that we proposed. Well, I'll also demonstrate the spatial combining in the upcoming slides that was actually carried out. Now, why? Why do we have to do this, or what is the advantage that this is actually going to give compared to a single wideband transmit chain? The thing is, because the problem of wide bandwidth is not related to just DACs there, because those who are basically transmitter designers will actually appreciate the fact that getting the RF power amplifier operate over wide bandwidths and trying to maintain the integrity of the output signal is essentially a challenge, because particularly in millimeter wave, the PA devices are made of compound semiconductors, which essentially exhibit greater memory effects at wider bandwidths. Now because of that, the digital pre-distortion block that is actually needed in the feedback also needs to be of wideband, because of the non-linearity of the PAs and the memory effects. So the non-linearity is essentially going to result in the form of a spectral expansion. Say if one has a channel bandwidth of B, so then the non-linearities, the third and fifth order non-linearities, are going to basically expand the overall bandwidth of the output signal to something like 5B. So which implies that one is actually going to encroach into the neighboring spectrum, which can result in legal actions. And secondly, when it comes to things like, say, SATCOMs, again, say, that's where usually the modulator remains indoor, and the upconverter and the output power amplifier remains in the in the outdoor unit. So one cannot actually do the sort of a switching arrangement, mainly to enhance bandwidth if needed. So the question is, one may ask, why do you have to increase bandwidth at all? Because you can see that even in the satellite domain, the present day high throughput satellites essentially can have bandwidths up to say 500 megahertz per beam. So whereas the legacy ones, usually the channel bandwidths are say below 60 megahertz. So now, but then satellite communication is an expensive business. So the cost of infrastructure is going to be quite expensive. I mean, if we salvage them, say, without using them for a long time. So one of the ways could be to basically use legacy equipment by interleaving them in, say, in frequency domain and say, and combining their outputs spatially. I mean, so the overall principle is that, I mean, we basically split the input signal into its frequency components and then distribute the frequency components into lower bandwidth DACs or modulators. Then take each one of them through the respective RF chain, amplify them, and then basically transmit them or radiate them spatially. I mean, sorry, combine them at the required point spatially. So here is the overall scheme. So the thing is, so what I was actually trying to say is that, so many such transmitters or of legacy designs could actually be interleaved spatially. I mean, could be interleaved in frequency domain and could be combined spatially at any required point. I mean, mainly to provide a feature of bandwidth scaling, or even things like bandwidth on demand. Now that was in case of say SATCOM signals, which are essentially constant envelope modulated signals. Now, how about dealing with terrestrial signals like say like OFDM? Because in OFDM, we are already modulating the subcarriers, and so it shouldn't be difficult to, I mean, to basically have, I mean, to basically extract the subcarriers, amplify them, I mean, upconvert them, amplify them individually, and then say combine them spatially. But this gives a specific advantage because one can see that if the spectrum is rectangular, basically the time domain signal is going to be a sink, and the height of the sink is proportional to the width of the rectangle. Means higher the number of subcarriers, greater is actually going to be the peak power. Now, greater the peak power, greater is the linearity needed from the RF power amplifiers. So, which is basically a circuit designer's, I mean, it's basically a headache to maintain both linearity and efficiency. So, by cutting down the spectrum or by cutting down the number of subcarriers to half or to any similar fraction, essentially one reduces the peak power. So then for the same input power, the amplification that actually one gets is basically at a higher efficiency. Uh, there is a study of this in one of the upcoming slides. So here is an experimental validation that was actually conducted, say, in a small lab facility. That's where, say, on the left side we have the two transmitting antennas, and this was specifically made wide beam, so that I do not actually have to apply beamforming weights. And on the right side, what you can actually see here is basically the receiving antenna. So initially, the test signal chosen for this, I mean, we initially went with a signal that was below 100 megahertz. I mean, so that could be demodulated by the equipment that was there in the lab. So this was essentially a 80 megasamples per second DVB S2 8PSK signal. So now since it's a single carrier modulation scheme, so the wave shaping is important. So a raised cosine, I mean, a root raised cosine filtering scheme was actually used for this. So which was, say, with a roll-off factor of 0.2. So thereby resulting in an overall bandwidth of, say, 96 megahertz. The original sample rate chosen for this was 200 megasamples. So now this signal was bandwidth interleaved into two transmitters of, say, I mean, whose clock rates were 100 megasamples per second. And the final carrier frequency chosen for this was 28.9 gigahertz. So this was the output spectrum. And this was the over-the-air measured output constellation. So one can see that it's actually comparable to what was obtained from a single wideband transmitter. So in the spectrum here, one can see that the signal in green, I mean, the spectrum shown in green was actually the spectrum of the signal that was transmitted from a single wideband transmitter. And the black was basically, it was the lower interleaved half. The blue was the higher interleaved half. So when the two were combined at the receiving antenna, we got back the original spectrum. Now, since we succeeded with the 100 megahertz case, well, because practically all equipment today, I mean, all say 5G equipment at least today are capable of generating 100 megahertz. What about higher bandwidths? So now this was the next thing that was actually tested. Now, initially, the reason why a single carrier modulation scheme was actually chosen was that this is more sensitive to any discontinuities at the intersection of the two parts of the spectrum. Because in case of OFDM, we have individual subcarriers, and then at the center, we have a null. So the individual subcarriers can still retain the modulation. Whereas here, since it's a single carrier wideband modulation scheme, the continuity of the phase and gain, the phase and amplitude of the spectrum needs to be maintained. So so if that could be maintained, if that could actually work for a single carrier wideband modulation scheme, so then it would definitely work for OFDM. So initially, a 400 megasamples per second 8PSK modulated signal was generated, and initially it was transmitted with a single wideband carrier. Say that's where it was actually sampled at 1 gigasamples per second. So then the same was generated using, say, two parallel transmitters of half the bandwidth and half power. And of course, the carrier frequency was maintained at 28.9 gigahertz. One can actually see the spectrum and the demodulated output constellation here. Now, since my equipment, the vector signal analyzer, was not capable of, say, demodulating a 400 megahertz wide signal, so I had to actually collect the IQ, the down-converted INQ samples from the internal quadrature down converter, then basically save them onto a file and then say perform the demodulation on MATLAB here. So this was an over-the-air measurement. This was not a conducted measurement. Say the RMS EVM was, say, 6% post equalization, and this was actually over the air. Now, there is an interesting use case of this. Say, since I said that it's a single carrier modulation scheme, which is very sensitive to discontinuities in any part of the spectrum. The thing is, if the beamforming is not done appropriately, or say, if one tries to basically capture a signal using an unintended receiver, then one is actually going to receive this, which is going to be garbage. So it also has a potential to basically provide a degree of security in the physical layer. So now, having demonstrated with a single carrier wideband modulated signal, the next objective was to show its feasibility for commercial terrestrial communications like 5G. So here, 5G NR signal was actually generated, say with a channel bandwidth of, with an overall sample rate of, say, 491.52 megasamples per second. So this, looking at the ratio of, so in a 2048 point OFDM, in a 2048 point FFT, so 1416 data subcarriers would basically correspond to an effective bandwidth of 355.2 megahertz. So now, without forward error correction, so well, typically we won't use anything without without an appropriate framing and without any without any appropriate forward error correction blocks. But then the objective here was to demonstrate the capability of the scheme. I mean, to to show the bandwidth interleaving with spatial combining. So there was no FEC applied. So basically, there was a transmission rate of say 2.032 gigabits per second to be achieved. So an over-the-air measurement was again done using a Rodenschwarz signal analyzer. And here is the received constellation. So one can see that actually the EVM is below 3%, say, and with an over-the-air measurement. Now, so here is the advantage that I mentioned earlier. The thing is actually, if we reduce the number of subcarriers in the OFDM signal, and say if we amplify them individually and then combine them, essentially each one can be more efficient. That's primarily because you can see the difference in the peak to average power ratio. Say that's where the red actually gives the signal. It gives the PAPR of the original OFDM signal, and then the blue and black. Well, of course, blue is not seen because black is overlapping on it. So you can see that the PAPR, the peak to average power ratio, is actually down by 2.5 to 3 dB. So which implies that you can reduce the back off needed in the RF power amplifiers by this extent. So now, since you have a reduced back off, means you can take the operating point, say closer to the saturation region, which implies that you're actually going to have a higher efficiency, a higher power efficiency. Now, if this is combined, say with other status quo peak to average power ratio reduction techniques, such as peak windowing or any of the frequency domain techniques, like say like partial transmit sequence, selective mapping, etc., one can actually improve the efficiency further. So the conclusion here is that the proposed scheme is basically, it demonstrates a scheme that's where the output is comparable to that. That's where the signal generated and transmitted is comparable in quality to that generated by a single wideband transmitter. So now here comes the reason of, say, having a review of the scheme here. The reason we had to do this is because the thing is, if you are going to integrate the entire transmitter, because as on today, the most mature technology, say for, which can actually handle both mixed signal as well as RF, is essentially Cmos. So then, if you are able to integrate the mixed signal components along with the power amplifier array here, so then I think we can actually have an operating product, say, which can actually do bandwidth interleaving or bandwidth scaling just by spatial combining without the need for any combining circuits. Well, let's get back into the structure here. Now, what one can actually see is just the power amplifiers here. So now, say if each one of these is actually driven by, driven by this half bandwidth RF chain or a quarter bandwidth RF chain. So then, essentially, multiple such, say 4 of such chips can actually, accomplish the task of, generating generating or transmitting signals with bandwidths of multiple gigahertz. Instantaneous bandwidths of multiple gigahertz. Because as on today, we depend on, say, time interleaved DACs, of course. But then, now as we go up higher in frequencies, obviously the jitter is going to be a major concern. With the higher clocking rates. So one of the ways to mitigate that would be this frequency domain signal generation and interleaving and combining them spatially, because particularly when it comes to applications like millimeter wave communications, even the standards say that the parameters have to be measured over the air or on a specific beam. So in such scenarios, I feel, it's my sincere opinion that spatial combining can play a major role. Now, along with the PA technology, but say with advancement in antennas as well, so one can actually improve the efficiency. So particularly when it comes to applications like, say, like bandwidth on demand, and say, considering a scenario, for example, that's where, say, a specific user, say, is at the periphery, of a cell. So now, that's when he or she is actually going to see a relatively low signal to noise ratio. So now when the signal to noise ratio is actually low, so then to have the same throughput, one needs to actually basically back off the modulation scheme. Say, instead of going with 64 QAM, like, say, for example, if one goes with QPSK, so then, because 64 QAM essentially has 6 bits per symbol, whereas here we only have 2 bits per symbol. So then for the remaining 4 bits, the only way that we can actually do is either extend the transmission time, or if the transmission time is critical, or if it's a mission critical sort of application, so then we only have to expand the bandwidth. So now if we have to expand the bandwidth, so then say, providing that high bandwidth or wide bandwidth all the time is going to be basically an extra burden on the power handling. So then schemes like, say, bandwidth interleaved modulators or bandwidth interleaved transmitters as a whole could be of application there. So that's where, if something is not needed, so then one can just turn it off, or one can actually allocate that to, say, to transmit, say, signals to another user in a base station. So this is all I currently have for this session. So any questions will be welcome.
Hi, Prasid. This is Sandeepan.
Yes, Sandeep.
So for spatially combined beams that you showed earlier, the first presentation,
Correct.
what could be the sources of noise and losses?
Correct. Very nice question. So, well, let's get back to that, or let's get back to one of the structures that was actually studied. Yep. So now, if one actually looks into it, so one can see that the efficiency of your amplification here essentially depends upon the efficiency of the dipoles. Of these electrically small dipoles in collecting your signals, and similarly, it also depends upon the efficiency of the output dipoles in transmitting those signals towards the output horn. So some of the sources of noise will actually be the losses incurred in this area. Along with that, since a waveguide is a metallic structure, so the quality of machining in the in the structure, like, say, like surface roughness, for example, they're actually going to cause conductive losses in the in the structure as a whole. So any loss in the input may be may be considered, say, as a part of rising the noise floor of the entire system. So yes, so these are essentially the I mean, these are essentially the sources of noise along with the noise figure of the device. So, well, so these structures are not, I mean, these are not, say, recommended, or I don't think they are currently suitable for applications in LNAs or low noise amplifiers. So these are primarily applicable in, I mean, in the last stages of the transmitters. That's mainly the PAs. That's where you actually, I mean, want to have high power.
Mhm.
But
Okay.
then, of course, I mean, even there, the efficiency. I mean, because you don't want to kill the efficiency there. So, I mean, the quality of the device will actually be. I mean, the quality of the entire structure will be determined by. I mean, by the surface roughness. I mean, or the machining ability, the horn antenna, gain, as well as the apertures of the. I mean, or as well as the efficiency of the receiving and the transmitting apertures connected to each of these.
Okay.
But well, as you can see, I mean, guys at Lockheed Martin have been able to achieve, say, overall combining efficiency of something like 70 to 90%. I mean, which implies that they've actually done a good job.
Okay. Okay. Thank you.
Welcome. So here is a more recent publication. That's where I mean, this is still spatial combining in a waveguide, but then instead of using a hollow metallic waveguide, they're actually using a planar SIW, or substrate integrated waveguide. Well, of course, I mean, since it's in a dielectric, it's not going to be as efficient as this one. I mean, as the metallic waveguide. Well, anyhow, it has matured actually. It has matured from the day it was invented, because we can see that companies like Corvo have actually commercialized such projects. I mean, such products.
I proceed. This is Madhav here.
Yes, Madhav.
So one question on a frequency interleaved scheme that you're proposing there. So you will also have ACLR regions for each of those spectra that you're trying to combine, right? So is this practical for like a contiguous spectrum allocation, or do we require it to be separated? I mean, non-contiguous allocations. Is that only feasible with that scheme?
Well, it is applicable to contiguous. I mean, that's a reason actually it was first experimented with a continuous. I mean, with a single carrier modulation scheme here. So you can see that essentially the ACLR of this falls here, and the ACLR of this actually falls here.
Okay, but that is low enough to not cause
Yes,
EVM degradation and things like that, is it? Is that
correct.
okay?
So one can actually see that, say in the OFDM case, the measured EVM, say, I mean, this is about 3.2% for a
Okay.
64 QAM signal.
Okay, but I mean, if I compare it with the time interleaving case,
Right.
is that pretty much comparable with what you would get with a time interleaved system, or
Well, it should
is
be
it
better.
slightly
Well, I mean, it should be
better
slightly
or
better in
worse?
my opinion,
Okay.
because the reason is because in a time interleaved case, so you actually don't have any. I mean, the mechanism that you actually have to correct for clock skews, between the interleaved stages is quite minimized. Well, let me just go back to the diagram. Like say, for example, if you have the clock distribution circuit here like this, and say if you have the analog mux here, so then the exact timing of the mux, that actually, I mean, which activates, say, one of the two parts, uh, is actually critical to the quality of the signal that you're trying to generate here. So now, if there's a clock skew, say, in the timing between the two, so then mitigating that is not going to be as straightforward as in the frequency interleaved case, because the frequency interleaved case, so any component falling in the adjacent band can actually be visualized as, say, as something like a two input and two output system. So then basically you can derive its, say, mmWave transfer function and invert that. So there have been publications on that.
Okay.
So it should all be doable in the digital domain. I mean, by, say, with a software correction.
But your time interleaving and all of that happens in the baseband, right? So then it's, I mean, I could still have pretty decent clock skews for the baseband combining, right?
Correct.
Yeah.
But then the thing is,
So you're saying that the frequency interleaving will be more accurate than that baseband?
correct. Well, because the reason is actually any clock skew that you actually have here. I mean, because since you're not using the clock to put out your two signals, the thing is the two signals that you actually get, they may have skews, but then they are independent of of the mux here. So any skew here is actually going to manifest in the form of a phase shift. Do you agree?
Yep.
So that phase shift can be corrected by coordinate rotation of each of the path relative to the other. Like say for example, if we have if we try to generate a a single carrier wideband modulated signal, so then so one of the ways to identify such differences here will be to take the first difference, or essentially the first derivative of phases around the intersection area. So any such say skew, or any such discontinuity of say one relative to the other is actually going to manifest in the form of a spike there. So then all that one has to do is correct the phase of the second relative to that of the first.
Okay, thanks.
Welcome.
Any other question from the participant? Okay. If not, we'll conclude our session. Thank you, sir, for your wonderful presentation on the spatial combined RF system, a choice of millimeter waveform communication. On behalf of IEEE CASH Bangalore chapter, I, Dr. Jalaja S, is the chair of CASH chapter. So we'll thank you for the wonderful presentation, and also for your time, whatever you spend for this particular webinar, and also
Most
you
welcome.
showed the insight about your papers and how you work in real time. Maybe it will help for our researchers. Thank you very much, sir.
Sure, definitely. Well, feel free to contact me. In case further, in case you see further interest in any of these areas.
We are going to publish this recording in our website. If anybody is having any queries, we'll get back to you, sir.
Sure. Thank you very much, madam.
Yeah, thank you, sir. Thank you. Thank you, everyone. Thank you for the participation.
So thank you very much.
Thanks.
So wish you all a pleasant weekend.
Thank you, one and all. We'll wind up here. Thank you, sir.
Thank you.